Physical properties of alkanes have not really changed since you talked about nonpolar molecules in Gen Chem, since they're nonpolar, having only carbon and hydrogen bonds and only dispersion forces or London dispersion forces. Because they only have dispersion forces, they're going to have low boiling points and low melting points. And those boiling points and melting points are going to increase as the molecule size increases because you'll have greater opportunity for polarization. Of the electron clouds. And that, remember, I don't know if you remember that term or not, but polarizing just means that it's going to be more easy to induce a dipole into its neighbor. So remembering that London dispersion forces comes from inducing dipoles and instantaneous dipoles. And so the more electrons we have in our electron cloud, the easier it's going to be to polarize it. Remembering solubility, it means that like dissolves like. We're talking about polarity, so we're going to look for nonpolar solvents like toluene or diethyl ether, just to name a couple. So these are the properties of alkanes. There are some reactions that alkanes undergo. Alkanes don't undergo that many reactions, but they do undergo combustion reactions, which allows them to be a great energy source, as we discussed, like fuel. So these are going to burn in oxygen. This is a reaction you should have learned in Gen Chem. So if you didn't, that's what we're going to go over right now, okay? So in Gen Chem, you should have learned that when we react a hydrocarbon with oxygen, we always get carbon dioxide and water. It's just how much carbon dioxide and water do we get? Well, here we get 2 waters if we react and burn 2 oxygen molecules. We're going to get also 212 kilocalories per mole of energy. So this is our fuel source right here. So this is something that, like I said, a reaction you should have learned in Gen Chem. But if you didn't, it's easy to memorize this one. Any hydrocarbon reacts with oxygen to produce CO2 and water. And this is a combustion reaction. Now, not every combustion reaction is going to go to completion, is going to be a complete combustion, but we're going to only look at complete combustion right now, okay? So this says methane goes to oxygen, or plus oxygen yields CO2 and water. On the bottom we have propane. It's going to take more oxygen, but we're going to get more CO2 and more water and this is obviously water vapor because it's going to be at a high temperature. So we will have to remember how to balance equations. I'll go over it quickly on the next slide, but this is really the only type of equation you're going to have to balance. So here we have halogenation. This is the next type of slide that the next type of reaction that we can have. And when we halogenate a hydrocarbon, we get a haloalkane. Now on this slide, I'm going to show you what happens if we have an unlimited amount of heat and light and an unlimited amount, heat or light, I should say, of the halogen that we're supporting. So this is the only reaction I'm really going to be looking for. These other reactions can happen, but when you're doing this on the test or the quiz, you only have to show me what would be called the mono-substituted. There's an E there. Products. So mono-substitution will be what we're looking for here. So this is methane. Methane is going to react with chlorine, but it can't just react with chlorine right away. So this, if you remember the Lewis structure of chlorine, the chlorines are sharing those electrons in the middle. So they're going to break apart, and we end up with a chlorine, or 2 chlorine radicals, where we have that single electron. That's going to then attach to the carbon kicks out a hydrogen, and that's where we get this byproduct of HCl. So this is H, and the X would be whatever is the halogen that we're using. So it could be bromine, it could be iodine, fluorine, something like that. So when we go through this, we have methane reacts with chlorine. So methane reacts with chlorine to produce chloromethane. chloro for the substituent, and methane for the CH3. You don't have to name the inorganic byproducts. Methyl chloride is also a common name for this. You don't need a 1 here because it's always going to be at carbon 1. There is only 1 carbon in this molecule, so that's not required. So if we want, or if we have enough of these reactants, we can produce a di-substituted product as well. So the chloromethane comes down here, reacts with another chlorine, and produces dichloromethane, or methylene chloride. Dichloromethane is our IUPAC name. Methylene chloride is more of a common name. We'll talk more about that later. I'm not going to stick too much into that right now. And then we also have our hydrochloric acid byproduct. The dichloromethane comes down here. If we have enough, it reacts with another chlorine as long as there's heat and light present and produces trichloromethane. Trichloromethane is also known as chloroform, so don't breathe a whole lot of it or you will pass out. You can die. You can get a whole lot of brain damage. Not comfortable. It's not as easy as they show it in the movies, right? All right, so react with chlorine. We produce another one, which would be tetrachloromethane or carbon tetrachloride. This is probably how you learned how to name it in Gen Chem. This is our IUPAC following the rules that we learned today naming system. You may have noticed that you need heat or light. That's written above the arrow. Now this can be written as heat or light. It could be written as a specific temperature. You know, it could say 100 degrees Celsius or, you know, don't quote me on that. It could be a triangle, which also means heat. This could say UV for light. There are a lot of different options, but if those are missing, that means this reaction will not go forward. It must be there for the reaction to take place. If they're not there, it's not going to happen. So we have to have heat or light, and I did not mean to do that. I don't know how to get back. Aha! Woohoo! All right, heat or light is necessary. So I want you to practice, pause it, practice. I want these to be balanced, so make sure you're balancing at least the first one. And I want you to show all products in this reaction. So what we would get from this one, we know the products are CO2 and water. We just don't know how many. So if you don't remember, we have 2 carbons on this side, 6 hydrogens, and 2 oxygens. Over here, we need 2 carbons, so we put a 2 there. We have 2 carbons. We have 2 hydrogens for the moment, and 2, 4, 5 oxygen. So I need this to be 6. I'm going to put a 3 there. That makes that a 6. Right, so now I have 2 carbons, 6 hydrogens, 5 oxygens. 2 times 2 is 4, plus 3, I now have 7 oxygens. But everything else is balanced. I have 2 carbons, 6 hydrogens, and 7 oxygens. So what I really need here is 7 halves. But I can't keep that, right? So I can put and get rid of a fraction by multiplying everything by the denominator. So this would be a 2. 7 halves times 2 is 7. I change this 2 and this 3. I'm going to multiply them both by 2. So this was a 2, it becomes a 4, and this becomes a 6. Now let's go through and recount. So that's just a trick. Maybe you forgot or weren't taught that trick, but it's a trick. It works with hydrocarbons a lot. 2 times 2 is 4 carbons. 2 times 6 is 12 hydrogens, and 7 times 2 is 14 oxygen. Here we have 4 times 1 is 4 carbons. 4 times 2 for the oxygen is 8, plus 6 is 14, so 14 oxygen, and 6 times 2 is 12 hydrogen. So now we're balanced. These should be really the only equations that you have to balance that are difficult to balance at all this year, but the alkanes are that's probably the hardest part of it right there. Yeah, because most of them are going to be pretty straightforward that we're learning. All right, moving on. CH3CH3. What is this? Ethane. Ethane, it has heat or light present, so we're going to remove one of these and put a chlorine there. So CH3CH2Cl plus HCl. Now, you could keep going and replace all of those, but I would be fine with that. I was just showing you that. 1, 2, you could also do it like this. That would also be the answer, just written in a line structure. Now, I wouldn't worry about going too far because we don't have more of the chlorine, but you would have to balance it out if you wanted to do what we did on the other slide. I was just showing you that was possible. So just doing one of them is fine in this case. All right, so heat or light is here. We've got bromine this time, so we're going to draw our cyclohexane, and we're going to say I'm going to remove this hydrogen and put a bromine there plus HCl. I'm going to erase all this so we can name them. So this was ethane, ethane, and cyclohexane. Right, this is carbon dioxide. We don't really need to know those right now because those are inorganic, and this is water. I mean, you need to know that, right? 1, 2, this would be chloroethane, and this would be bromocyclohexane. And you don't need a number for either of those because you wouldn't, anywhere you put them, it would still be carbon number 1. All right. Whoops, I gotta erase all this stuff. Click through. Practice, pause it, practice, give me the answer. This one's hard. I want to see if you can do it. It's really not that hard. You can do it. All right, so if we write this in, I want you to pause it. Make sure you pause it and do it, okay? This is a carbon, has 1, 2, 3 bonds, so it must have 1 hydrogen. These are all CH2, 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 CH2. So I have 1, 2, 3, 4, 5, 6, 7 carbons. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. Oh, that's next to the oxygen. Sorry, I didn't mean to write that. C7H14 is what I meant to write down there. Let's double check and see if that makes sense. Okay, so if I have C7, 7 times 2 would be 14. And in this case, I don't add 2 because of the ring. So this is a decent structure. It's possible to be I said structure when I meant formula. So this is a decent formula. It's possible, so it's probably correct. So C7H14 is our formula for this ring. That's really helpful when moving forward, so you don't have to keep trying to count the rings. So don't be afraid to make things easier for yourself. Our products are going to be carbon dioxide and water. It's just how much of them, right? So we have 7 carbon, we have 14 hydrogen and 2 oxygen, 1 carbon, 2 hydrogen, and 3 oxygen. I put a 7 here, that becomes a 7. 7 times 2 is 14, plus 1 is 15. Then I need a 7 here. 7 times 2 is 14 hydrogen. All right, and 7, so I have 7 times 2 is 14 plus 7 is 21 oxygen. So 21 halves again, because this is a 2 and I'm not going to be able to get that in half. So I multiply everything by 2 again. This happens a lot in with hydrocarbons. I'm just going to make a different color. 2. So I divide 21. So 21 divided by 2 times 2 is 21. I hope you agree with me. Math skills, right? Math skills. 21. All right, 7 times 2 for both of these is going to be 14. And let's double check. So always, if you have time, double check. I have 14. Oh, go back. I'm not sure why I did that. 14 carbons, because 2 times 7. I have 2 times 14 is 28 hydrogens, and 21 times 2 is 42 oxygen. 14 carbon, 14 times 2 is 28 plus 14 is 42 oxygen and 28 hydrogen. Now, one thing you want to do is double check and make sure that you didn't multiply by 2 when you shouldn't have. So we have an even number, a 2, an odd number, a 21, and 2 even numbers. So this is not divisible by 2. So we didn't make a mistake in that one, which is good. All right, so practice. I'm not sure if your slides have the heat or UV, so double check, make sure it's there, make sure you write it in. I want you to pause it and do these slides, please. Do these answers. Balance where necessary. You only have to show a mono-substituted product. Again, because I'm only giving you 1 chlorine. I'm not going to give you more. So 1, 2, 3, 4. You want to ask yourself, how many sets of equivalent hydrogens are there? I have 1 set here. These are equivalent hydrogens. And these are equivalent hydrogens. What does that tell me? How many products can I have? It means I can have 2 products for this one. 2, 3, 4, 2, 3, 4. Now, I can put the chlorine here. That's the green one. Or I could put the chlorine here. Either side, it doesn't matter. So this would be my green product. And this would be my yellow product. No matter which way I do it, it's going to be, I'll name them for you. This is, let's highlighter, sorry. 1 chloro. You know, I'm going to move that over. 1 chloro butane. And this would be 2 chloro butane. Now, why do I need a number here when I didn't need a number for the ethane? Is because I do have an option of having 1 or 2. I can't just say 1 because it could be either. Now let's look at the next one. In this one, how many sets of equivalent hydrogens do I have? Well, if I took one of these CH3s, one of the hydrogens from there, or here, I would get the same result. If I took the hydrogen from here, I would get a new result. And here, and here. So I actually have 1, 2, 3, 4 possible products in this, even in just a mono-substituted way. So let's write these out. 1, 2, 3, 4 chain, 2, 3, 4 with a methyl group here. 2, 3, 4, my methyl group. 2, 3, 4, methyl. 2, 3, 4, methyl. So if I do the yellow one first, I would be adding my chlorine either here or at the top, either way. If I do the green one next, it would be here. Next it would be here, the blue one, and the purple one would be here. So I'm going to highlight those so you can see what they are. This is my purple one. This is the blue one. This is the green one. And these, there would be 2 possibilities, right? But they would be the same, so we don't have to write them both. And let's name them. I went to the highlighter again. Keep doing that. Right? 1, 2, 3, 4. Remember, this is not a carbon here. It's a chlorine. So I have a methyl and I have a chloro. So these ones are harder to name. which comes first alphabetically is chlorine. So I would say 1-chloro, 2-methyl butane. Here I can go 1, 2, 3, 4. And both of my substituents are at 2, but chlorine comes first. So 2-chloro, 2-methyl butane. Here, 1, 2, 3, 4. Oh, it turned to black. That's interesting. Well, apparently red plus blue equals black. Let's see, 2-methyl, 3-chloro, but the chloro still has to get written first. So 3-chloro, 2-methyl butane. And here I have 1, 2, 3, 4. And again, this is not a carbon, it's a chlorine. So here, do I say 2-methyl, or should I be numbering 1, 2, 3, 4? Oh, sorry. I don't want to mess you up. You can do that numbering. I'm going to get rid of that highlighting because it's hard to see. 1, 2. I feel like I'm... Here, let me just get rid of this for a minute. Let's do it in 2 different colors. So I can say 1, 2, 3, 4, which would give my methyl group a 2. Or I can say 1, 2, 3, 4, which gives the methyl group a 3, but it gives my chlorine a 1. So I am actually going to go with the green numbering system, which says 1-chloro, 3-methyl butane. So that is just a reminder on naming, and I'm going to go through these slides. You can read them at your own, pause it and read them. These are just notes about reactions, notes about reactions, how they're important. You're going to want to make them an important part of your practicing. Practice them every day. They're cumulative, so by the time we get to the end of the semester, you're still going to have to know about them, because even if the final isn't cumulative, you're still going to have to understand these reactions to be able to do this stuff. So as we go throughout the organic chapter, for sure, you're going to have to be able to do all these types of reactions. So keep a list for the reactions, and have like a piece of paper or something like that that you go through each day and you practice them and you don't forget them. Use flashcards, something like that. However you learn, try to do it best. Try not to just memorize them all. There's just too many to memorize. Some of you are going to have excellent memories. I know that, and maybe that's better for you, but I'm not going to say you can't do that. I can't ever tell you how you can and can't learn, right? So whatever works best for you. So haloalkanes. Haloalkanes is what we've been talking about. We can halogenate these alkanes, but then comes the question, just because we can do something, should we? Well, are they okay? Well, they're safe in the lower atmosphere. They're actually non-toxic, non-flammable, odorless, non-corrosive. So why are they so bad? Why did we want to ban them? Well, 1 CFC chlorine, so one of these, just one, can destroy up to 100,000 ozone molecules in the stratosphere. So why are they so bad? Because they're not reactive enough and they make it to the stratosphere. And so when they make it to the stratosphere, one of these destroys 100,000 ozone molecules and creates a hole in the ozone layer in the process. So we first noticed a hole in the ozone layer in the early 80s, I think, maybe the late 70s we started talking about it. I can't remember the exact year, but the hole started forming over Antarctica. So whose problem is it, right? I think it's all of our problems. So we really need to make sure that we're taking this seriously. We still use them. There's a lot of air fresheners, shaving cream, refrigerants. It was manufactured as Freon, but now we've tried to make it better. Just so you know, the word ozone in Greek actually means smelly, because ozone is actually a very strong odor, but we do really want it. It's good for us. It keeps us away from UV rays and all of that good fun stuff. So why is this important? Because it's all of our problems. You want to make sure if you're changing out the AC in your car, you don't vent it into the atmosphere. One of these molecules can destroy up to 100,000 ozone molecules. So yes, you are making a difference if you do this in the wrong way. So the US EPA thinks that if we continue down this path where we've gotten rid of most of these, that we'll have the problem fixed by 2050. However, what was the solution? Well, the solution was to come up with HFCs, which are hydrofluorocarbons, and HCFCs, which are hydrochlorofluorocarbons. But, okay, this one was the first replacement they came up with. But a significant fraction of these still make it to the stratosphere, and when they break down, we have a chlorine buildup that they actually didn't originally predict. So now we have more chlorine. But and I'm just going to go on to the next slide. So we have a chlorine in these. So you see HCFC 141b has now been replaced by HFC 134a, which is better because it has no chlorine and it has excellent thermodynamic properties. So it's actually a really good product. Right now, we don't know of any big problems it's making. But so it's used in place of CFC12 in automobile ACs and mobile AC systems in Australia and the United States. So the EPA thinks that if we return or if we get rid of these products that we shouldn't be using, that we should be able to return the ozone layer to normal by about 2050. But the world has to comply with what's called the Montreal Protocol. I spelled protocol wrong, seriously. My contact just flipped in half. All right, so if you want to look that up, go ahead. I'm not going to waste your time if you already know what it is. So there you go. Go ahead and look it up if you're more interested in it. It's good for, look, how can we be better for the environment? It's always better for everyone. So next up, you're going to see a naming review. I'm not sure if I did end up putting this in your slides, I think, but if not, you can pause it and you can look through these. These are just the naming review slides that I made just to remind you, because this is really important. This is going to continue. So if you need to pause, go back, review it. We're going to keep moving on from there.